Refraction. What refraction is? A change in direction. I really can't spell today, so let's try this again. Direction of light due to a change in speed of light. Why would the speed of light change? It's due to a change in the medium. Medium. So the only reason light will change speed is if it changes medium. In other words, if it's traveling in air and then it moves into water, the speed of light will change. So just like with sound, the only thing that determines speed of sound was the medium. The only thing that can change the speed of light is the medium. A couple things we need to know, and I will draw all of this out so you can see what this looks like. We're going to draw diagrams for refraction. And the first thing you need is a normal line. And a normal line is a dotted line that is perpendicular. Remember back to forces, normal meant perpendicular, so again, it's the same idea. A normal line is a dotted line perpendicular to the change in medium. You're also going to have the angle of incidence. This is the angle between an incident ray and the normal line. And we call the angle of incidence theta 1. And again, you'll see this as soon as I draw out what this looks like. Next thing we have is the angle of refraction. This is the angle between the refracted ray. It should be a C. Refracted ray and the normal line. And the symbol for the angle of refraction, theta 2. Okay, so what does this look like, what I'm talking about? You're going to have, when we draw these diagrams for refraction, you're going to draw a line. This is the change in medium. We call this 1 and this 2. So 1 just means incident. In other words, where does it start? And 2 refers to the refraction. So the first medium that you start in, that's why I call it 1, and then the medium that you go to, that's why we call it 2. The normal line is a dotted line perpendicular to the change in medium. So this line right here is the change in medium. You're going to have your incident ray that comes in. It's going to cross at the normal line, and then you're going to have your refracted ray. So this would be the incident ray. This will be the refracted ray. And then your incident angle and your angle of refraction. So the incident angle is between the incident ray and the normal line. This is theta 1. Your refracted ray is between the refracted ray and the normal line, so that would be theta 2. The biggest mistake I see with these is not putting these angles in the right place. So again, it's between the normal line and the ray itself. You're not going here, you're going here. So once again, with refraction, you have an incident ray that refers to the first medium you're in. It crosses over the change in medium and goes into the second material. This would be your refracted ray at the angle of refraction. So let's look at how light rays behave when they move from different mediums. And this is something you're just going to have to know. If you're moving from slow to fast, so in other words, what's going to happen here? Your angle of incidence is going to be less than your angle of refraction. Your ray is therefore going to refract away from the normal line. So think Fran. Fast refracts away from normal. Fran, F-R-A-N. what that will look like. We'll just do this up here. You've got your change in medium and your normal line. Your incident ray comes in. So this is your theta 1. Your refracted ray has to be greater than your incident ray. So in other words, theta 2 is larger than theta 1. So Fran fast refracts away from normal. What that means is you went from a slow medium to a fast medium. And you'll see me writing slow and fast to remind myself. If you're moving from fast to slow, so this is the complete opposite, theta 1 is greater than theta 2, the ray refracts toward the normal line. So the complete opposite happens. You've got, I'll do this a little bit smaller. So if you're moving from a fast medium to a slow medium, you've got your incident ray, and then your refracted ray will be toward the normal line. So again, this is theta 1, theta 2 is that little one in there. Okay, so the main thing you need to remember is Fran fast refracts away from normal if it's going from a slow to a fast medium, or just in general. Whenever you're in the faster medium, this angle has to be farther away from the normal. Okay, let's now look at index of refraction. I don't know why those are there. Let's get rid of those. Okay, so the index of refraction is a ratio, and it's the ratio between the speed of light in a vacuum to the speed of light in a medium. So the symbol for index of refraction is a lowercase n, and it's a ratio, so it's not really much of an equation. N equals C over V. So N is the index of refraction. V would be the speed in a medium. So this is speed of light in a medium. And this C is a constant. Right down here, C is the speed of light in a vacuum. So it's the constant 3 times 10 to the 8th meters per second. And that's a number you can store in your calculator as C. So that is the same everywhere in the universe. It's essentially what we use for light in air. Air is thin enough that we consider it a vacuum. So all the index of refraction tells you it's the ratio between the speed of light in a vacuum and the speed of light in a medium. Since nothing travels faster than the speed of light, N cannot be less than 1. It's just not possible for the speed of light to be less than anything else. There's nothing that travels faster than the speed of light. Okay, so now we're up to Snell's Law. What Snell's Law does, it describes the relationship between the angle of incidence, the angle of refraction, and the index of refraction. The equation's fun. N1 sine theta 1 equals N2 sine theta 2. So 1 refers to the incident medium and 2 refers to the refracted medium. So it's a fairly simple equation to use. N1 sine theta 1 equals N2 sine theta 2. And this brings us to the last thing we're going to look at, total internal reflection. So total internal reflection occurs only when light passes from a slow medium to a fast medium. If a critical angle is reached, no refraction occurs, and all light is reflected back into the slow medium. So what is a critical angle? Sine of the critical angle is equal to the refracted medium over the incident medium, where N1 has to be greater than N2. So, and just a note on these ends, a higher index of refraction means a slower medium. So in other words, what happens in total internal reflection? The light can't get out, it essentially gets trapped. Diamonds have a fairly high index of refraction, so you have light that comes into the diamond and then it can't get out, so it just reflects in. That's why they're so shiny. Same thing with fiber optics, and we will see with the demo how that's working. The critical angle is reached, the light can't get out of the medium, so it just reflects back in. And this is not in the notes, but something you do need to know is the angle of reflection. So this is reflection, not refraction. Always equals the angle of incidence. So in other words, we have, here's a change in medium, so N1, N2, here's the normal line. You have an angle here, so this would be your incident ray. So you have a ray that comes in and it doesn't refract. The reflected angle, call that theta r, should be equal, and that was not drawn to scale. So the angle of reflection is always, 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 always equal to the angle of incidence. Okay, so I'll do one example. If you want to see more, then there's 3 here. So I will do a total of 3 examples, and then we'll be doing practice in class, but at least watch the first one. Here's our first example. A ray of light in air enters a clear ice cube where the index of refraction is 1.31 with an angle of incidence of 60 degrees. What is the angle of refraction? And then what would the angle of refraction be if it were traveling in water, where the index of refraction is 1.33 when it reached the ice cube? So let's draw our diagram. Here's our change in medium and the normal line. We're going from air into an ice cube. So from air into ice. Air is always going to be your faster medium because air is essentially a vacuum. So I like to make a note, this is fast, so this is going to be slow. The angle of incidence is 60 degrees. So here's our incident ray coming in at 60 degrees, and then it's going from fast to slow, so it's going to refract towards the normal. And this would be my theta 2. Okay, given information. We know that the index of refraction for air, and you'll get a list of what these are, and I forgot to mention, the index of refraction for air is always going to be 1. So N of air is always equal to 1. Because air is essentially a vacuum, it's thin enough that it can be considered a vacuum, so for C over V, that ratio would be 1. It enters into the ice cube, so we're going to call that N2. Because it's your refracted medium is 1.31. My angle of incidence, theta 1, is 60 degrees. And we are looking for the angle of refraction, so that would be theta 2. And then part B, if your N2 is 1.33, we're looking for the theta 2. all we're going to do is use Snell's Law. N1 sine theta 1 equals N2 sine theta 2. Looking for theta 2. So isolating this, N1 sine theta 1 over N2 equals sine theta 2. It's a very easy equation to use. N1 for air was 1. It's unitless since there's a ratio. So 1 sine of 60 degrees over 1.31 equals sine theta 2. 0.661 keeps on going equals sine theta 2. So the inverse sine of that number, so inverse sine of 0.661 keeps on going, is going to give me my angle. And that answer is 41.38 keeps on going degrees. We had 3 sig figs, so theta 2 is approximately 41.4 degrees. One clue that this is a good answer: fast refracts away from normal. So we were going from fast to slow with the behavior of rays. Fast to slow means that theta 2 has to be less than theta 1. So 41.4 degrees is less than 60 degrees, so at least the behavior is making sense. Let's look at part B now, where we're looking at the different index of refraction. I'm just going to skip down to this step right here. So we've got N1 sine theta 1 over N2 equals sine theta 2. So 1 sine 60 degrees over 1.33. And if we just combine this all in one step, so the inverse sine of all of that equals theta 2, we get 45.11 keeps on going degrees. Again, it's still less than the incident ray, that makes sense. So if we're in water instead of ice, theta 2 is about 45.1 degrees. If that makes sense, we're fine. You can stop now. I'll do 2 more examples in case you want to see those. A light ray traveling in air enters a transparent substance at an angle of 40 degrees. It is refracted at an angle of 25 degrees. How fast does light travel through the substance? So here's our diagram. We have an incident ray coming in at 40 degrees, and then it refracts at an angle of 25 degrees. And we are moving from air into an unknown substance. But remember, air is always going to be fast into a slower substance. So slow refracts towards the normal. Listing our given and find. We know that theta 1 is 40 degrees. Theta 2 is 25 degrees. We're looking for the speed of the substance in 2. So we're looking for the speed. I'm going to start with Snell's Law. N1 sine theta 1 equals N2 sine theta 2. We know that N1 for air, we know both the angles, so what we're looking for here is N2. N1 sine theta 1 over sine theta 2 equals N2. So 1 sine 40 degrees over sine 25 degrees equals N2. So sine 40, and again, make sure your calculators are in degrees, over sine 25 gives us 1.52, keeps on going for N. We know that the index of refraction equals the speed of light in a vacuum over the speed of light in a substance. So speed will equal C over N2. This equals 3 times 10 to the 8th, that's the constant C, divided by that number, 197 243,189.8 meters per second. And this was 2 sig figs. So the speed is about 2.0 times 10 to the 367th meters per second. And this should be 8, not 7. One giant clue here, if you're ever solving for speed, if you get anything greater than 3 times 10 to the 8th meters per second, you made a mistake because nothing can go faster than the speed of light. Let's do one more example. The speed of light in clear plastic is 1.9 times 10 to the 8th meters per second. A ray of light strikes the plastic at an angle of 22 degrees. What angle is the ray refracted? So here's our change in medium. We have, let's assume, air and then plastic. So going from fast to slow. Here's the normal line. The ray comes in at an angle of 22 degrees, and then it's going to refract into the plastic. Because we're going from fast to slow, we know that this angle has to be less than 22 degrees. Given the speed in plastic is 1.9 times 10 to the 8th meters per second, and that the angle of incidence, so theta 1, is 22 degrees. We're looking for theta 2. We'll start with Snell. N1 sine theta 1 equals N2 sine theta 2. So here we know theta 1, we know N1, we don't know theta 2, and we don't know N2. But we do know that the index of refraction is equal to the speed of light over the speed in a substance. So this equals 3 times 10 to the 8th meters per second over 1.9 times 10 to the 8th meters per second. That gives us 1.57, keeps on going. So now we know N2, looking for theta 2. Theta 2 equals the inverse sine of N1 sine theta 1 over N2. So this equals the inverse sine of 1 sine 22 degrees over 1.57, keeps on going. And we get inverse sine of, let's see, sine 22 13.72, keeps on going degrees. So theta 2 with 3 sig figs is about 13.7 degrees. This number again is less than the incident ray, as it should be because we're moving from fast to slow. So that's Snell's law. We'll do practice problems with this tomorrow. You have 3 examples here, and then we'll move on to lenses.